Welcome back to the deep dive. Today we aren't just unpacking a topic. We are literally shifting our timeline.
Right.
I want you to do something for me. It's a mental exercise. Look at the dashboard in front of you, whether you're in your car or at your desk or walking the dog.
Just picture it.
Imagine the date on that display doesn't say today's date. It says Friday, February 20th, 2026.
We have officially jumped into the future. And honestly, looking around in 2026, the automotive landscape feels drastically different from the early 20s.
It really does. And we're doing this time jump because the transition we have been talking about for a decade, the shift to the software-defined vehicle, or SDV, it's no longer just a PowerPoint slide in a boardroom.
No, definitely not.
It's no longer a vision.
Yeah.
It is here.
No.
It is now the industrial reality.
That is right. If you look back at where the industry was around, say, 2023 or 2024, there was a lot of ambition, a lot of buzzwords. Everyone wanted to be the next Tesla.
Oh, for sure.
But by 2026, the rubber has hit the road, literally and figuratively. The old way of building cars. That hardware-driven waterfall V model where you bend metal first and sprinkle some code on top later, that is effectively dead.
Dead. That is a very strong word for an industry that has been around for a century.
Well, that had to die because we hit what the industry calls the complexity wall.
The complexity wall. I mean, it sounds like something out of a sci-fi novel. What does that actually mean for a car manufacturer?
It is basically a math problem. The amount of software code in a vehicle grew by a factor of 100 in just a few years. We are talking about vehicles with over 100 million lines of code.
Wow.
To give you some context, a modern fighter jet usually has less than that. You simply cannot manage 100 million lines of code using processes that were designed for stamping door panels.
Right, because those are two completely different engineering disciplines.
Exactly. So the solution was a massive and honestly painful but necessary shift to software first and agile DevOps.
And that brings us to our mission for this deep dive. We have a massive stack of research here. Technical strategy reports, compliance documents, white papers on everything from Linux kernels to particle simulation.
It is a lot of material.
It is. And our goal for you listening is to answer one fundamental question. How do you decouple a car's soul, which is the software, from its body, the hardware?
Exactly. And to do that, we aren't just going to list off some trends. We're going to break this massive technological stack down into 9 distinct pillars.
Right. The outline calls them modules. Are we going strictly MECE on this?
That is the management consultant in me coming out. Yes. MECE, mutually exclusive, collectively exhaustive. We are going to dissect the vehicle from the architecture down to the digital twin. 9 pillars that explain how a car company transforms into a tech giant.
I love that structure. It's like an anatomy class for a robot. Let's not waste any time. Let's jump straight into the first pillar.
Let's do it.
So Module 5.1 SDV architecture and business model reconstruction. This feels like the foundation. If you get this wrong, nothing else really matters, right?
This is the absolute foundation. Before you write a single line of code, you have to change how you think about the car itself. In the old world, let's say 2015, the car was a mechanical product with some computers hidden inside.
Right.
In 2026, the car is a digital terminal.
A digital terminal, like a smartphone on wheels. I know people in the auto industry hate that analogy because it kind of oversimplifies the engineering. But is it accurate here in terms of the architecture?
It is accurate in terms of architecture. The core logic here is what we call hardware abstraction.
Let's unpack that. Hardware abstraction sounds super technical.
Yeah.
What does it actually look like in practice?
It means the software, the application layer, the thing that decides how the car drives or what music it plays. It doesn't really care what specific chip it is running on. We have moved to a service-oriented architecture, or SOA.
SOA. I have heard this term used heavily in cloud computing.
Exactly. The car industry effectively just stole the cloud industry's playbook. In SOA, hardware capabilities are exposed as services. Think of it this way. In the past, if you wanted to turn on the windshield wipers, there was a specific physical wire connected to a specific electronic control unit, an ECU.
Okay.
And that sent a specific electrical signal. It was hard-coded.
So if you changed the wiper motor to a different brand or changed the ECU, you essentially had to rewrite the code or totally change the wiring harness.
Precisely. It was a marriage and not a happy one. It was extremely rigid. Now, wiper control is just a service. It is a piece of software that broadcasts to the system I offer the service of clearing the windshield.
Oh, I see.
And any other piece of software can call that service without knowing if the wiper motor is made by Bosch or Continental or what chip controls it.
So it's kind of like previously, if I wanted a pizza, I had to drive to a specific shop and talk to a specific guy named Luigi.
Right.
But now I just open an app and press pizza, and the system handles who makes it and how it gets to my house.
That is a brilliant analogy. The pizza service is abstracted from the pizza maker, and because of this abstraction, we see containerization. Just like in cloud computing with Docker, these vehicle functions are packaged into containers.
Microservices.
Yes, microservices that can run anywhere. They can run on the central computer, they can run in the cloud during testing, or they can be moved to a completely different zone of the car if needed.
And this technological shift creates the business shift, right? Because if the software isn't glued to the hardware forever, you can change it later.
This is where the money is. This is the decoupled life cycle. This is the holy grail for automakers today. Historically, if you wanted a better car, you had to go buy a new car.
Right. My navigation system from 2014 looks like an 8-bit Nintendo today. It's totally embarrassing.
Exactly. The hardware and the software aged together, they rotted together. But now the software lifecycle is completely independent. You might buy a car with level 3 autonomous driving hardware like LiDARs, cameras, powerful chips.
But the software isn't ready yet.
Right, the software is only ready for level 2 when you drive it off the lot. Over the next 3 years, through over-the-air updates, or OTA, that car literally grows into a level 3 vehicle in your driveway.
Which fundamentally changes how car companies make money. It is not just about the day I drive it off the dealer lot anymore.
No, we are moving from point-of-sale revenue to lifecycle revenue. We are seeing companies like Stellantis back in their Dare Forward 2030 plan projecting billions in revenue.
What were their numbers exactly?
The target was 20 billion euros by 2030, coming purely from software subscriptions and on-demand features.
That is a staggering number. 20 billion euros is the size of a Fortune 500 company just sitting inside the dashboard.
It is massive, and it forces a software-first R&D process. You cannot wait for the physical prototype to be built to test this stuff. If you wait for the metal to arrive, you are already 2 years late.
So how do they do it?
You have to build the software on virtual platforms before the silicon chip is even manufactured. By the time the metal is stamped in the factory, the software has already been running virtually for months.
So the vision has moved from technological ambition in 2024 to industrial scale delivery in 2026.
That is the exact headline for Module 5.1.
Okay, so we have established that the car is a platform, but a platform needs a nervous system. It needs a way to organize its thoughts. That leads us right into Module 5.2, AUTOSAR.
Right, AUTOSAR, Automotive Open System Architecture. This is the middleware standard. It is the glue. But in 2026, we have to distinguish between two very different types of AUTOSAR. We have the classic platform and the adaptive platform.
I have heard this described in the engineering community as muscle versus brain.
That is the perfect way to visualize it. The classic platform, or CP, is the muscle and the spine. It handles the hard, real-time, safety-critical stuff.
Give me an example of hard real-time. Why is that distinction so important?
When you hit the brake pedal, you need the calipers to clamp down on the rotors within milliseconds. Not around milliseconds, exactly milliseconds every single time without fail.
Yeah, I definitely don't want that system buffering or doing an update or thinking about the meaning of life while I'm trying to stop.
Exactly. You want it dumb, fast, and obedient. So the classic platform is static. It is written in C language. It uses signal-based communication like CAN bus or LAN. It is rigid, but it is incredibly reliable. It runs on microcontrollers, which are small, low-power chips that do one thing perfectly.
Okay, so that is the muscle. What about the brain?
That is the adaptive platform, or AP. This is for high-performance computing, or HPC. This is where your autonomous driving algorithms live your connectivity, your rich infotainment.
The complex stuff.
Yes, this environment needs to be highly dynamic. It needs to handle huge amounts of data. It uses C++ or even Rust, and it runs on a PSX operating system, something like a stripped-down Linux or QNX.
And the big shift here isn't just that we have both muscle and brain, but how they actually talk to each other, right?
Correct. We are moving from static signals to service-oriented communication. We mentioned SOA earlier. The protocols here are things like SOMI IP, which is scalable service-oriented middleware over IP and DDS.
DDS, Data Distribution Service. Why does DDS matter specifically for the listener?
Because it allows for dynamic discovery. In the old days of CAN bus, every single message on the network had to be predefined in a master document. Message ID 101 is engine speed. Message ID 102 is steering angle.
Okay.
If you added a new feature that needed to know the engine speed, you had to reprogram the whole network map so it knew to look for ID 101.
Which sounds like an absolute nightmare for updates. If I update my radio, I do not want to accidentally brick the engine controller because the map changed.
It was impossible for rapid updates.
Yeah.
With DDS, a new app can just come online and ask the network, hey, who has the engine speed? And the service providing it says, I do. And they just connect. It allows for dynamic resource allocation.
It sounds like a cocktail party versus a roll call. In a roll call, everyone speaks in a rigid order. In a cocktail party, you just find the person you need to talk to and start a conversation.
That is a great comparison. And this dynamic allocation is essential if you are doing those frequent OTA updates we talked about. You can't update the car if the network breaks every time you change a single line of code.
And standardization here is key across the industry, right?
Crucial. It allows apps to be portable. You do not want to reinvent the wheel or the brake controller for every new model year. Before AUTOSAR, every Tier 1 supplier like Bosch or Denso had their own proprietary way of talking to the network.
Total mess.
Now that plumbing is standardized, car makers can focus on the differentiation, the unique features rather than just reinventing the plumbing.
All right, so we have the architecture and we have the middleware. But cars aren't just gadgets. They are 2-ton machines hurtling down the highway. People's lives are quite literally at stake. How do we ensure this agile, fast-moving software is actually safe? That brings us to Module 5.3, ASPICE.
ASPICE, Automotive SPICE. It stands for Software Process Improvement and Capability Determination. It is essentially the rulebook for quality.
But the challenge was, how do you maintain safety when you are updating software every week in an agile workflow instead of every 3 years like in the old waterfall days?
Yeah, safety usually implies slow down and check everything twice, while Agile says move fast and break things.
You definitely do not want to break things in a car.
No, you do not. So we saw the evolution to ASPICE 4.0. This was a massive game changer because it formally included hardware engineering, or HWE, right into the assessment.
Wait, ASPICE didn't cover hardware before? That seems like a huge oversight.
Not explicitly in the process assessment model in the same way. There was a huge disconnect. You would have code that was perfectly compliant on paper, but it didn't actually match the physical capabilities of the specific ECU it was going on to.
So the software engineers were sprinting and the hardware engineers were running a marathon.
Exactly. ASPICE 4.0 bridges that gap. It actively solves the disconnect between the code and the physical reality.
And I see in the notes there is something here about machine learning too, MLE.
This is huge. As we put more artificial intelligence into cars, we desperately needed a process to govern it. You cannot just throw a neural network into a car and hope for the best. ASPICE 4.0 added machine learning engineering.
What is the golden rule there?
The separation rule. You explicitly have to separate your training data from your test data.
Basically, you cannot grade your own homework.
Exactly. If you train the car to recognize stop signs using a specific set of 10,000 photos,
No.
you cannot use those same photos to test if it works.
Because it will just ace the test from memory.
Right. It will score 100%,
Right.
but it might fail completely when it sees a new stop sign out in the real world that it hasn't memorized. You need complete independence, and you need traceability.
Traceability, is that like keeping a paper trail of the code?
Yes, but for complex logic.
Oh.
It is the whole black box problem of AI. If the car suddenly decides to swerve, you need to be able to trace that specific decision back to a requirement and a test result.
But in the past, traceability was just a massive linear document, right?
Right. Requirement A connects to line of code B, which connects to test C.
That sounds manageable until you have 100 million lines of code.
Then it becomes a bureaucratic nightmare. So we are moving to cluster-based traceability.
What does it mean in practice?
Instead of a massive linear list, we use clusters. We treat a logical group of functions as a cluster and trace the relationships between those clusters at a higher level. It perfectly fits the agile speed without drowning the engineers in endless paperwork.
It sounds like organizing a huge library by genre and topic rather than trying to list every single word in every book in alphabetical order.
That is a very fair comparison. It is all about managing complexity through hierarchy. It allows automakers to be fully compliant without being paralyzed by the process.
All right, let's move down the stack to the operating system itself. We touched on Linux earlier, Module 5.4 software Linux, and mixed criticality safety.
This is what I like to call the castle defense strategy. Here is the fundamental conflict. Linux is amazing. It has thousands of open source contributors. It is highly flexible. It runs all the rich apps we love. But it's frankly terrible for safety certification.
Why is that? Is it unstable?
It is not that it is unstable. It is that it changes way too fast and it is just too big. The Linux kernel has millions of lines of code. You literally cannot verify every single line to ASIL-D standards.
ASIL-D being the highest safety integrity level.
Right. It would take decades to certify, so instead of certifying the Linux kernel, we build a massive wall around it.
Isolate and monitor.
Precisely. We use a technology called a hypervisor.
Like running Windows on a Mac desktop.
Similar concept, but embedded deep down in the silicon chip. The hypervisor, often using the Vertio standard, runs directly on the hardware. It creates completely separate partitions.
Yeah.
In one partition, you have your life-critical stuff, the brakes, the steering. That is running on a highly safety-certified RTOS, or real-time operating system like QNX.
And in the other.
In the partition right next door, but completely physically isolated, you have Linux running your Netflix, your maps, your fancy user interface, usually something like Android Automotive.
And the hypervisor ensures that if Linux crashes during a movie,
the brakes still work. This is called freedom from interference, or FFI. If the infotainment system goes into a complete blue screen of death, it physically cannot take memory or CPU cycles away from the braking system.
But what if Linux doesn't just crash? What if it starts sending crazy commands across the network, like turn up the radio volume to 100 or worse, display a map that says turn left directly into a brick wall?
That is exactly where the safety monitor comes in. It is a Guardian component, usually rated AC-DIB. It constantly watches the Linux partition.
Like a chaperone.
Exactly like a chaperone. If Linux starts acting weird or freezes or sends illogical commands, the Guardian sees it and immediately triggers a safe state. Maybe it just reboots the Linux partition, or maybe it shuts down the display entirely. But it absolutely prevents that error from propagating down to the wheels.
And this mixed criticality setup is what finally allows car companies to fully use open source right.
Yes, and the economics of it are incredibly compelling. By using automotive-grade Linux or AGL and Eclipse SDV standards for the non-differentiating plumbing.
The stuff the customers never see.
Exactly. Manufacturers save up to 30% of their total R&D costs.
30%? That is wild.
It is massive savings. They've finally stopped building their own proprietary operating systems for things that do not matter to the brand identity.
Right. Nobody buys a Ford because they really love the file system directory structure.
Exactly. They buy it for the driving experience. So you use standard open source plumbing and you spend your money on building an amazing experience.
Okay. 30% is a massive chunk of change in the auto industry. So we've got the OS sorted. Now, how do we actually build the apps? How do we write the code fast enough to matter? That brings us to Module 5.5, Agile CI/CD.
This is the massive shift from a physical workshop to a software factory.
I really love that term,
Cool.
software factory. It really implies huge scale and precision.
It really is a factory. We are talking DevOps pipelines like Jenkins or Zool, and the biggest technological enabler here is a concept called bit parity.
Bit parity. That sounds pretty technical. Can you break that down for us?
Sure. In the old way, you wrote code on your powerful engineering PC, which uses an x86 architecture like an Intel or AMD chip. But the actual car uses an ARM chip.
So they don't speak the same native language.
Right, so you had to cross-compile or translate the code.
Like translating a really complex novel from English to French.
Exactly. And as anyone who has ever used an online translator knows, things get lost. You would fix a bug on your PC compile and push it to the car, and the bug would still be there.
Or a totally new one would magically appear because of the translation.
It was a complete nightmare. So what is bit parity? It means we use servers in the cloud, specifically things like AWS Graviton, that are also natively ARM-based. The cloud architecture matches the vehicle architecture exactly bit for bit.
So the cloud is a perfect digital mirror of the physical car chip.
Exactly. Zero translation errors. If it works in the cloud, it is guaranteed to work in the car. And this allows for continuous verification.
How does that look in the daily workflow of a developer?
Imagine an engineer saves a piece of code. Ideally, in 2026, that save instantly triggers an automated pipeline. First, static analysis checks the basic grammar. Then ASRA checks ensure it strictly follows safety coding rules.
And
Then it checks structure coverage like MCDC. Finally, it automatically runs on a virtual ECU in the cloud with fault injection.
all automatically.
100% automatically. The engineer gets feedback in minutes. Hey, you just broke the turn signal logic.
That is incredible. In the old days, they might have waited weeks. to get an hour of time on a physical test bench just to find out they made a typo.
Now we are running thousands of virtual tests in parallel. It changes the entire engineering culture. It moves from we hope it works to we mathematically know it works. It removes all that dead waiting time. The data shows a 100x speed up in testing cycles.
A 100x speed up, that completely redefines how fast you can innovate.
Absolutely.
Speaking of knowing it works, we have talked a lot about code. But cars exist in the real physical world. They have to deal with pouring rain and wind and snow and extreme heat. How do we simulate actual physics with this kind of speed? Module 5.6, Design CAE.
CAE stands for Computer-Aided Engineering. But we aren't just doing basic 3D crash tests anymore. We are moving pure physics into pure math. The real star here is SPH, Smooth Particle Hydrodynamics.
SPH. Outline calls it mesh-free simulation. What does that mean?
Traditional simulation requires you to draw a mesh, a structured grid over the object you are studying. That works fine for mapping airflow over a smooth metal hood.
Because the hood doesn't change shape.
Right, but it is really hard when the object is water splashing violently or snowpacking into a weird shape. The mesh gets completely tangled and the math breaks down. SPH abandons the mesh. It simulates the fluid as millions of individual freely moving particles.
It's like a giant ball pit.
A ball pit with millions of tiny physics-accurate balls that interact with each other in real time.
So you can simulate what exactly? Driving through a massive flood.
Water weighting exactly. You can precisely simulate how the water splashes up into the engine bay where it might short out a critical sensor. You can simulate snow accumulation, how wet slush packs into the wheel wells and freezes, potentially blocking the steering column or blinding a LiDAR sensor.
And you can do all of this without actually building a prototype car and driving it into a snowbank in Sweden.
Right. You do it entirely in the computer. And it goes even deeper than weather. We are using it for oil cooling inside electric motors.
Yeah.
You can visually simulate how the liquid oil flows over the complex copper windings to cool them down under heavy load.
There's a huge manufacturing angle here too, right? I saw some very specific
Oh,
memory.
absolutely. This is where AI meets heavy industry. We use high-fidelity modeling to predict thermal stress during manufacturing. For example, when you use GMAW, which is gas metal arc welding, to weld a steel chassis together, the immense heat naturally warps the metal.
Right. Metal expands when it gets hot.
In 2026, we use AI to precisely simulate that exact welding process beforehand.
So the factory robot actually knows the metal is going to warp before it even strikes the arc, so it welds slightly differently to counteract it.
Exactly. It dynamically predicts the deformation and optimizes the physical clamping force and the welding path. We have concrete data showing this predictive process improved commercial production line efficiency by exactly 6.01%.
6.01%. That is an incredibly specific and massive gain for a factory running 204/7.
And it reduced equipment downtime by 87.56%.
That is just staggering. An 87% reduction in downtime. That is basically eliminating the whole concept of machine breakdown on the line.
It really is. It is optimizing the physical creation of the car using high-fidelity math before a single spark flies.
Okay, so we have designed it, we have simulated the physics, we know how to build it. Now we desperately need to validate that it drives safely in unpredictable real-world traffic. Module 5.7 validation.
Here is the core issue, the scale problem. You simply cannot drive enough physical road miles to logically prove an autonomous car is safe. You would literally need to drive billions of miles to randomly encounter every freak accident.
Right, like a piano falling off a truck or a child running out from behind a park van in a blizzard. If you tried to do that physically, you would be driving test cars for hundreds of years.
Correct. So we go right back to the cloud scale simulation. But we do not just manually write out test cases. We use AI to automatically generate edge cases.
So the AI is actively trying to trick the car's driving logic.
Essentially, yes. The AI looks at the driving logic and says, what happens if I make the sun glare hit the front camera at this specific 42-degree angle while a cyclist is aggressively merging into the lane? It generates millions of these crazy variations in parallel.
And this massive scale relies on industry standards too, right?
Yes, specifically ASAM standards, Association for Standardization of Automation and Measuring Systems. They use something called Open Scenario, which is a domain-specific language, or DSL, to strictly define these logical scenarios.
So how does that save time?
You define a cut-in scenario just once. Car A cuts in front of car B, and the computer automatically multiplies it into thousands of concrete variations, different speeds, different weather conditions, different road friction coefficients.
And this connects directly to SOTIF.
SOTIF, yes. Safety of the intended function. This is a critical concept to understand. ISO 26262 covers functional safety like a brake line snapping. But SOTIF isn't about something breaking. It is about the system working perfectly but still failing because the real-world situation is just too confusing.
Like the sun glare example earlier. The
Yeah.
camera isn't broken, it is just blinded by the light.
Exactly. Or maybe the front radar sees a metallic plastic bag blowing across the road and thinks it is a solid rock, so it violently slams on the brakes. That is a SOTIF issue. We validate that the car behaves safely in these highly confusing states purely in the cloud long before a physical prototype exists.
We are effectively front-loading the safety verification. It is amazing how much is done before rubber touches the road. It seems like the physical road is just the final exam, but all the actual studying happens in the cloud.
That is the perfect way to summarize it. The road is just confirmation.
But eventually you do have to test the real physical components.
Yeah,
Module 5.8 testing and the X-in-the-loop matrix.
right. There are absolutely some things you still need to verify physically, like the final electric motor calibration. But even here, we have broken the traditional bottleneck.
I read about active DOE in the notes. Active design of experiments. How does that work?
This is fascinating. Calibrating an e-motor used to take 8 full weeks running it on a dyno, a physical test bench. You would have to manually run the motor at every possible speed and torque combination to map its total efficiency. It is a brute force grid approach.
Which sounds boring, slow, and incredibly expensive.
It is. Active DOE uses AI to essentially gamify it. The AI runs a few initial points, looks at the data trend, and dynamically decides which points are actually interesting to test next.
Interesting meaning what?
It skips the boring, predictable, linear parts and hyper-focuses on the boundaries, the specific places where the motor might overheat or start vibrating strangely.
Oh, I get it. It is like a game of Battleship. But the AI is smart enough to know where the ships are likely clustered, so it doesn't waste time taking random shots at the empty ocean.
Exactly. Renault used this exact methodology and reduced their physical motor tuning time from 8 weeks down to just 4 weeks. They cut the required measurement points by 30 to 50%.
That is a massive efficiency gain for a legacy automaker.
Eh.
And then there's the Xyle matrix.
X in the loop. Ideally, you want a perfectly seamless transition. You always start with software in the loop or SIL running entirely in the cloud. Then you move up to hardware in the loop hill, where you plug the real physical ECU board into a massive simulator. Finally, vehicle in the loop fill.
And the notes mention shadow mode. I find this one really clever.
Shadow mode is brilliant. It is using the customer's actual car as a silent test bench. You deploy a brand new algorithm, say a new emergency braking logic. You push it to 100,000 customer cars via OTA, but you put it in silent mode.
So it doesn't actually hit the brakes.
Right. It receives all the real-time sensor data from the highway, and it pretends to brake. It calculates exactly what it would have done, but it doesn't actually physically intervene, but it secretly records that data.
And then the engineers compare that to what the human driver actually did.
Or what the old legacy algorithm did. It is test to learn versus test to pass. You gather complex, real-world edge case data from millions of miles of driving without risking anyone's safety.
It effectively turns the entire global fleet of cars into a massive parallel research lab.
Precisely. It allows you to validate a huge update across millions of real miles in a few days. Because of this whole matrix, we are seeing a dramatic reduction in physical prototype needs by 20 to 60% across the board.
Which perfectly leads us to the final pillar, the culmination of all of this engineering. Module 5.9 digital twin and the zero prototype strategy.
This is the ultimate strategy, the absolute holy grail for OEMs. Zero prototype means the explicit goal is to completely sign off on the car's safety and performance before the very first physical prototype is ever built.
Wait, zero. You build the first physical car and it is just done.
Ideally, yes. Or at least the first one you build is purely a confirmation prototype, not a development prototype. You aren't building it to see if it works. You are building it to legally prove that it works to the regulators. This massive shift compresses the traditional new car development cycle from 3 to 4 years down to under 2 years.
And this relies entirely on the executable digital twin, right?
The XDT. It is not just a pretty 3D CAD model that looks like the car. It is a physics-accurate, code-accurate replica running continuously in the cloud. It runs the exact real binary code that will go into the physical car.
The market for this specific technology must be huge.
It is exploding. By 2030, the global digital twin market is projected to hit $149.8 billion.
Almost $150 billion. That is a massive industry just for virtual copies of things. But for this to actually work, You need absolute trust in the math.
That is the operative word, trust. The industry has rigorously moved to a metric called zero uncorrelated simulation.
Explain that metric for us.
It means if the virtual simulation says the car stops in exactly 30 meters and the real physical car stops in 32 meters, the simulation is officially useless. It has to match perfectly. We are aggressively moving from engineering judgment, where a senior engineer looks at a graph and says, yeah, looks good to me, to quantified quality based on ASAM QSQ metrics.
And are the safety regulators actually on board with a car that was tested entirely in a video game, essentially?
They are now Euro NCAP 2026, the major European safety rating agency. They officially started allowing virtual testing data to count towards the real 5-star safety ratings. That was the huge tipping point. When the regulator legally accepts the simulation, the financial need for crashing 50 real cars completely disappears.
That is a fundamental shift in how human beings create complex machines. It sounds almost risky to skip the physical tests, but if the math is truly perfect.
If the math is perfect, reality is just a formality.
So let's zoom out. We have covered the 9 pillars, from the core architecture to the middleware, the rigorous compliance, the massive software factory, the particle simulation, and finally the digital twin. What does this all mean for the listener? If I am buying a car in 2026, or if I am working in this industry, why do I care about any of this?
For the consumer, it means your car is no longer a rapidly depreciating asset in terms of its technological capability. It actually gets better with age, it gets smarter, it gains totally new features, it becomes tangibly safer. You do not have to trade it in every 3 years to get the latest tech.
And for the industry itself?
It is purely about survival. Companies that stubbornly cling to hardware excellence, perfect panel DAPs and beautifully stitched leather. If they do that without mastering these 9 software pillars, they will quickly become just hardware contract manufacturers for the tech companies that do master this.
They will just be the Foxconn to someone else's Apple.
Exactly. The soul of the car has officially become exponentially more valuable than the body, and we are seeing the clear winners and losers emerge right now based on how well they execute these 9 specific modules.
I want to leave our listeners with a thought based on that. You mentioned the executable digital twin is effectively the master product.
Yes, it is the gold standard source of truth.
If the digital twin is the absolute master, and the physical car parked in my driveway is just a physical instance printed from that digital file, does the physical car even matter during the development phase anymore? Or are we entering an entirely new era where heavy manufacturing is just hitting a print button for the software we've already perfected in the cloud?
That is the multi-billion-dollar question of the decade. If the simulation is truly perfect, reality is just a formality. We really aren't building cars anymore. We are building massive software factories that just happen to produce cars.
A literal print button for cars. On that somewhat mind-bending note, we are going to wrap up this deep dive into the software-defined vehicle. Thanks for taking this time jump to 2026 with us.
It was a pleasure to be here.
See you next time on The Deep Dive.